Hi everyone, in this video I'm going to talk about the use of mathematical functions in economics. So if you're coming from the Basic Math Skills for Economics playlist, I spoke very loosely about functions in a previous video and I told you guys to let me know if you want a more formal account, and it looks like you do, so thank you to the user who commented on that previous video. Now, functions are a big topic in mathematics, and I'm only going to be covering the issues that I understand to be important for students of economics. Actually, that's the only experience I have, and it will be a beginner treatment of the subject. So I'll discuss the sort of things that helped me understand what's going on, especially with the notation, and really very abstractly, we can start with the idea or the picture that a function is a black box. We're going to put in an input or inputs into the black box. Some stuff happens in the box with that input. This stuff will be like a set of instructions or a set of rules, and you get an output back after that stuff happens. The stuff that happens in the box, so the instructions or the rules, that will depend on the form of your specific function. This whole system will function to relate our input or inputs to an output. So that's very abstract. Let's look at an example. Say if we have f of x is equal to 2x plus 2. So this notation is communicating that we have a function f. So f is the name of the function, the name of our black box, that has the input x. The input is what it will be in the parentheses next to the name of the function. And the specific set of rules or instructions, what happens in the black box, well, here we're given that we're going to multiply our input by 2 and then add 2. So in this case, we are told what happens in the black box. Our rules don't have to be in the form of an equation. You could have words describing instructions. It's a very abstract concept, the concept of a function. But in economics, often we do use equations, mathematical equations. Now we talk about the notation on the left-hand side. We have a function that is dependent on x, or we'll say f of x. That's how we describe the part on the left. Critically, the parentheses are not multiplications. They're just ways of communicating that the value of the function, so the output, depends on the input x. And what we can do is we can evaluate our function at different values of our inputs. So if we wanted to evaluate f of x here at x is equal to 2, then we can have the following notation. We could have f, open bracket, 2, close bracket, like this, is equal to 2 times where we have x, we'll put 2. So 2 times 2 plus 2, which is equal to 6. So this is how we notate that we're evaluating the function at a specific value of the input. So we've mapped our input 2 to the output value 6 by way of our function f. Now our function and our inputs can have any name and they can represent lots of different things. So we could have g of x or h of y and t, so we can have more than one input. And we can have economically significant variables and notations, so we can have a total cost function with the input being quantity, for instance. Now, in addition to this, often we might add, often it's implied or it's explicitly stated that y is equal to f of x. And this can be a bit confusing. This second equation just functions to explicitly name our output as y. And it also tells us explicitly what y depends on. So the inputs that we need in order to find our output y. And that can be a really useful piece of notation. So there are sometimes two equations associated with one function, but to make it more confusing, sometimes there's not. So when there's not an equation like y is equal to f of x, we're just going to take f of x to be equal to the output. That's what we're naming our output. And this means, very roughly, if we were going to use our Cartesian plane to map our inputs and outputs, we're going to draw out our function. Well, 2x plus 2 would be like this, and y would be our output if we had y is equal to f of x. But if we didn't see y is equal to f of x, or we had nothing like that, we didn't know what to name our output is just f of x. That's fine. People use this system of notation like that as well. Now, further to this, in economics, in my experience, the use of these notations can be slightly different depending on the context or the use. So depending on what the author wants to communicate, and different authors might be doing slightly different things, but usually you can figure it out from the context and it should be consistent. So I have some examples here that I found in some textbooks that I have. So invariant, for instance, let's do this one first. And I've put the references for each of these texts below. If we had u, open bracket, x1, comma, x2, close bracket, is equal to x1 to the power of c times x2 to the power of d, this tells me that we have utility, which is a function of, so x1 and x2 are defined as the amount of good 1 and good 2 that we're consuming in the text. And the specific instructions associated with this utility function to get our output, that's how much utility we're getting, is we're going to raise these amounts of good 1 and good 2 to c and d and then multiply them together. So here we're given a specific form of the function. We know what happens in the black box. Here also there is no other statement akin to y is equal to f of x. So I just know that the output is utility, and that's it. So that's pretty common that we see stuff like this in economics. I'll show you another one. How about Blanchard and Sheen? This is an interesting one. We have the demand for money is equal to nominal income, that's the $ times y, multiplied by a function L of the interest rate. So here we're not given a specific form of the function. So the function is really a black box and we don't know the instructions, but the authors have put a constraint on what that function has to look like. That negative sign underneath tells us that whatever the function is, there has to be a negative relationship between interest rates and the demand for money. So interest rates decrease and demand for money increases, or the interest rates increase and the demand for money decreases. So that's another nice little example of how we might use the notation and functions in economics. All right, let's look at the second example from Varian. I chose this example because I wanted to show you what happens when we're asked to evaluate a function at specific points. So this is from part of the text that discusses the definition of economic rent. So we have price times output, and we're at the optimal levels because of the asterisks, those stars. And here we take away costs, but we don't have a specific form for costs here. Again, it's just a black box. But we're told that we're going to evaluate that cost function at the optimal output, that y star. So we're not being told the exact form of the function, but we are told that we're talking about a situation where we're evaluating that cost function at a very specific input. All right, the last one from Blanchard and Sheen, I chose this one because this is more like y is equal to f of x, that real statement of what counts as inputs to a specific output. So we're told C, which is consumption, is equal to the function, the consumption function, which is dependent on disposable income. So really this is just a formal statement that tells us that consumption is dependent on disposable income, and the plus sign here just tells us that there must be a positive relationship between consumption and disposable income. If disposable income goes up, consumption goes up as well. If disposable income goes down, consumption goes down as well. So hopefully those examples showed you a little bit about how we might use functions and how we might notate what we're doing. And I think in economics, we are pretty fluid in our use of these descriptions to a degree, but really that functional notation just makes it really easy to describe and talk about abstract models. We often don't give you the specific rules. We don't tell you what's in the black box, but we want to talk more broadly about the properties of such models. And really, indeed, it might not only be until you see a practice problem or an exam where you see things like the specific form of the function. Now, the other thing to note is that not all equations are functions. Specifically, for an equation to be a function, each possible input, so each x value or combination of inputs, if we have many inputs, must correspond to only one output value of y. So that's that abstract idea of a function, that if we have some inputs, that will lead to a definite output. It can't be ambiguous. So if we consider an equation like x squared plus y squared is equal to 2, this is actually the equation that makes the shape of a circle on our Cartesian plane. And here you can see for these x values, our input values, some of these correspond to two y values. So our inputs track to more than one output. So this is not a function. And this is probably definitely the other reason why economists really like functions, apart from just being useful in terms of notation. Really, the whole idea of a function is that it tracks inputs to outputs. In order to find a specific output, what we need to do is we just need to know our inputs, and that will lead us to our output. And this makes functions really useful in mathematical modeling, in particular when we want to understand the determinants of economic phenomena. If more than one output value is associated with a single input value or single input values, our model will not be able to predict or describe or simulate very well. It would be ambiguous. So we like to restrict what we're working with to functions in order for our models to be more usable. Now, to check if an equation is a function, we can do what we call the vertical line test. So we're going to draw the function in question on our Cartesian plane. We put the input variable on the horizontal axis and the output variable on the vertical axis, and we draw a line vertically down through our diagram, like I'm doing here with x squared plus y squared is equal to 2. And if our vertical line hits the diagram twice, like it does here, then that means that a single input value is associated with two output values in this case. So that tells us that the vertical line test has failed and we're not dealing with a function. So I've never known this specific thing to be a requirement for students to know or for a student to demonstrate the vertical line test or anything like that. But I do think it's kind of good to know, and I was taught it. All right, now it is worth saying as well is that we can add or subtract functions together. So if we had g of x and f of x, we could add them together. And this means, if I think about an example from economics, if I had, say, a total cost function which was equal to 5q squared plus 2 times q, I can actually think of this function as being composed of two separate little functions added together. And sometimes it's useful to think about the equations that we work with in this manner so that we can apply different rules of calculus. So often our rules of calculus are formulated and communicating in terms of functions. So we can multiply functions together, so we can think of g of x and times f of x, and we can divide them, so g of x divided by f of x. We can have also what we call composite functions. So we can have a function, let's say g, which is a function of another function. So the input to our function g is another function, which itself is a function of x. Now this becomes important when we have what we call the chain rule in calculus, which we will do later. So I'll give you an example of a composite function. Let's say I had 5x squared, all raised to the power of 4. Well, I could think of 5x squared as f of x. And the function g then, well, let's just say that the output of f of x is equal to h. So g of f of x is actually equal to g of h, which is equal to h to the power of 4. And I do think it's good to notate it this way, explicitly defining h as the output of f of x, because notationally I just feel like f of x all raised to the power of 4 is, I don't know, it feels like a little bit messy. So I think that's why we always see that with the chain rule. Anyway, that's my take on the use of mathematical functions in economics. I hope that has helped. As always, thanks so much for watching my content. If you would like written notes to help you on your journey, or even just to support this channel to help me make more videos, you can visit my store. The notes include lots of practice questions with solutions, which can help you solidify your understanding of the skills discussed in these videos. Also, if these videos have helped, please like and subscribe, comment below, share all of that. Any feedback also is super welcome. Thank you so much for watching my stuff, everyone. Have a great day.